Swayam Prabha. Digital India. Educated India.
So, very good morning to everyone, those who are present in person and who are joining us from who are joining us remotely. So, I am Dr. Sagar Saurav. I am an assistant professor in the Department of Chemical Engineering. So, yesterday we started the course, and the first lecture that I delivered was on a brief overview of catalysis. So, we started with the history, and then we looked at what is the importance of catalysis in 21st century. So, there was a little bit of technical glitch. What I understood after delivering my lecture is that the online participants were not able to hear the voice properly. So, what we decided is that I will go over the slides that I presented yesterday such that everyone is on the same page, and then once we cover those portions in the initial 15-20 minutes, then we will go to the new things as planned for the today. Okay, so the outline for today would be that we will talk about the history of catalysis, then we see how catalysis has changed the quality of human life for the mankind in the 20th century, and then we will see how catalyst is going to improve both the environment and the humankind situation in 2021 in 21st century, and then we will go over a brief overview of the types of catalysts, their length scales, the length scale of the catalyst compared to the reactors and all, and then the nature of the active sites and how the active sites change during the reaction or different environmental condition, and then how we can tune these active sites such that the system works in favor of us. Okay, the catalysis just does not go back to some 50, 100 or 200 years, but if we look at it, it goes back to almost 10,000 years from now. So, the early days of catalysis were like brewing, where yeast or some enzymes were used to convert some fruit juice into wine or beer. Similarly, there were other examples where the catalysis was used for baking, where a small portion of the old dough which can be mixed to the new dough such that you can form the new sourdough. And similarly, it was used for the leather tanning processes, where a certain extract of a plant was mixed with the animal skin such that the skin's degradation was suppressed significantly. However, in those days the people were not aware that they were doing the catalysis, but nonetheless, the catalysis was always an inherent part of the humankind, and those catalysis they fall into the biocatalysis range. So, the modern catalysis starts somewhere around 1798, where the first example was shown by acid hydrolysis of the starch to form some sugar molecule, and this is the first example of homogeneous catalysis. And then there was heterogeneous catalysis, where oxidation and dehydration of ethanol was done. The dehydration of ethanol was done to form some ethylene, and this was done over alumina based catalyst, which is a great example of solid acid catalyst these days. However, the very first practical application for the catalysis part or to be specific, the heterogeneous catalysis, that came in 1823, but it was marketed in 1825 by the famous Duvernoyer. It is known as the Duvernoyer lamp, and here I am showing one of such pictures. And what happened is that you have a jar where you have the sulfuric acid present, and then you have a zinc ribbon which you can dip inside that sulfuric acid. Now, once you dip the zinc ribbon to the sulfuric acid, the reaction will start. Zinc will react with sulfuric acid to form zinc sulfate, but at the same time it will also produce hydrogen. Now, that hydrogen will go up to the surface, and there is a platinum gauge present on this portion, and there is oxygen present in the atmosphere. So, the hydrogen will react with oxygen in the presence of this platinum gauge to form a flame. So, that was the first instance when humankind was able to control and produce fire at its will. Before that, there was friction and all these things that was happening to create fire. Okay, and this approach was so famous that starting from 1825, in next 5 or 6 years, more than 1 million of such Duvernier lamp was sold throughout the Europe and all across the world. So that only suggests that how the simple catalytic reaction just changes how the fire can be created at will and can be used to our to serve our purpose. Now, coming to the modern days, the 20th century has seen a lot many examples where catalysis has helped humankind. The very first was related to the ammonia synthesis. These days, this ammonia is really important because we make fertilizers for ammonia, and that fertilizer help us grow more crops, which helps the 8 billion people to feed in the whole world. But at that time, the synthesis of ammonia was for a different purpose, because ammonia previously by Ostwald, it was shown that the ammonia oxidation can be done over the platinum type of catalyst to form nitric acid and nitrates, and those nitrates were actually used to form explosives, and those explosives were used for war purposes and all these things. And this is an example how over the year the ammonia synthesis catalyst has evolved. Initially, the energy required for the ammonia production was huge, but over the years how the catalyst was modified to have much higher efficiency. That means the energy input was much lower for the ammonia production, but still today it's a significant portion of our today's energy is going towards the production of the ammonia. Now, moving forward, there were few other cases. For example, in the 1920s, we have methanol synthesis over zinc and chromium oxide catalyst. We have Fischer-Tropsch processes where cobalt and iron oxide catalysts were used to convert syngas to valuable fuels and chemicals. So, these were the examples when the C1 chemistry started. Another example was the catalytic cracking of crude oil to form some transportation fuels and all, and then oligomerization of alkanes to produce high octane number fuels to improve the fuel quality and the efficiency of the engine. One more example was the ethylene oxidation to form ethylene oxide, which is then converted to ethylene glycol, which is used for many purposes, and the most significant one being the anti-freezing agent. And this was done over the silver catalyst, and to date also the silver catalyst remains as the main component for the ethylene oxidation reaction, although we have added few more promoters to improve the catalytic activity. Another great example was the polymerization, and this was proposed, established by Carl Ziegler and Guglionato, for which they were given the Nobel Prize. And at that time, the titanium chloride catalyst was used for polymerization of ethylene and propylene to polyethylene and polypropylene. So, and that was used for manufacturing for daily uses of plastics and all these things. And today's this is slightly modified with addition of magnesium chloride and currently being used. Another significant aspect was the discovery and then the synthesis of silico-alumino compounds, which are known as zeolites. Now, these zeolites have very specific structures. They are microstructural in nature, and then because of their fine structures, we can actually control the reaction as well as the selectivity towards different products. So, there is an extensive list that I have prepared where I have identified all the important milestones that has been achieved by the catalysis and how they have served the human kind in the 20th century. So, while at the end of the course we will be sharing the course material, I will share those additional documents for your reference as well. So, now that is the case for the 20th century. Now, see what are the typical areas where the catalysis has been used, and these can be broadly classified into 4 areas. One is petroleum and energy, that we know all our transportation fuel comes from the cracking of crude oil, and then we have commodity chemicals. So, all different kinds of polymers, adhesives, cosmetics, coating type of materials are there. Then we also look at the pollution control, because we have carbon dioxide, SOx and NOx, as well as the hydrocarbon that is being exhausted from the industrial flue gas as well as in your automotive exhaust, and we need a catalyst to convert them to a comparatively less harmful chemical which can be sent to the atmosphere. And then of course, the big part is also in the pharmaceutical and the food sectors, where we are looking at the medicine, beverages and dairy. Now these days we can see all manufactured products, among them more than 85% comes from the catalytic processes, and only 15% comes from a non-catalytic process. And if we look at the catalyst market, so $20 billion is roughly the current catalyst market, with a cumulative annual growth rate of about 4%, but the associated market is about 20 to 25 trillion dollar. Now comparing to the world's economy, which is close to $100 trillion, so the catalyst itself is contributing to 1/4 of the total economy. So that only tells how important is catalysis in our life, and how it is going to play a strong role in the future as well. So for the future, there are several challenges, because with rising population of the humankind and the depleting nature of the fossil sources, we need alternative way of generating fuels and chemicals. So those are the challenges for the catalysis science going forward in the 21st century. So the first one being the transition from the fossil to the renewable sources, as well as to develop the circularity, and that is reuse of some of the wastes like biomass waste or waste carbon dioxide, as well as the plastic sources, to form some fuels and chemicals. And also in the 20th century, while the catalysis was still in its developing stage, we used certain processes and chemicals which are not very environmentally benign. So in 21st century, as a responsible citizen, we need to like replace those hazardous chemicals with some hazard free and waste free, as well as energy efficient processes. So that is where the catalysis is going to do more in the 21st century. Similarly, we need some tools for interconvergence of energy, because we are going towards the renewables, where, say for one example, we are using the renewable energy for the water splitting to produce hydrogen. Now it's not just the hydrogen production, but it's also the storage and transportation of hydrogen, which is going to help us towards lowering the carbon emission. And then of course, only the science is not going to solve the purpose. We have to do it in an interdisciplinary approach by combining it with engineering, such that we can achieve more than what has been achieved till date. So let's just look at like some of the basic definitions of what is catalysis. So the first one was proposed by Berzelius in 1936, and what he said is that the catalyst possesses a special power that can influence the affinity of the chemical substance. That means it can break the chemical bonds and then make them convert to another type of bond. But in the modern day, the catalyst is something that increases the rate of attainment of the equilibrium without itself undergoing a change. But in the modern day chemistry, with like high end spectroscopic as well as different physical and chemical characterization techniques at our disposal, we know that the catalyst, which is considered to be unchanged for so many years, does actually change during the reaction, because they are experiencing a different environmental condition as well as the temperature as compared to the one what we are seeing these days, and the process is called catalysis. So what are the different types of catalyst? So a broad classification can be a homogeneous catalyst, where it can be an acid base type of material or the transition metal compounds. We can have heterogeneous catalyst, which can be within the bulk and the supported type of heterogeneous catalyst. We have some biocatalysts, which are like enzymes, some microorganisms and all these things, and we can have heterogenized homogeneous catalysts. So the homogeneous catalysts, they are put on the substrate such that their movement is restricted, and we get benefit from both the heterogeneous and the homogeneous part. Typically, if we look at the distribution of the use of the catalyst in industry today, more than 80% of the industrial processes, they rely on the heterogeneous catalyst, and about 17% on the homogeneous catalyst, and not more than 3% on the biocatalyst. Now with new processes being developed over the years, the contribution from the homogeneous catalyst is decreasing day by day, and that of heterogeneous catalyst is increasing. So, this course as we have designed it will mostly focus on the heterogeneous part of the catalyst. Okay. And these are some of the examples of these heterogenized homogeneous catalyst. So, one is like an immobilized metal ion. So, where you have a flat surface of high surface area metal oxide type of thing, and you have the ligands through which you can connect to the metal which are doing the actual reaction. And these are some of the examples here where we have the taught butoxide phase of moly tungsten or the rhenia, which are anchored to a high surface area silica support is shown as an example. So, on the other side we have the enzymes and cells, and they can be of different type. For example, on a substrate, these enzymes can be covalently bonded as shown here. They can be just Fiji-served, they can be in a cross-linked form, or they can be embedded within the polymer matrix or trapped within the polymer matrix, such that their distribution is pretty broad, and then the benefit out of these enzymes are more and more. Or it can be on a substrate where you have the products and the substrate and the enzymes just placed next to each other. Similarly, if we look at the heterogeneous catalyst, so there are different categories. On one hand, we have the bulk catalyst, that means either it is a metal or metal oxide, we have the full composition. Then just because the catalysis is a surface phenomenon where the surface of the substrate or surface of the active material is actually doing the chemical transformation, where the bulk is just there to improve the surface to bulk ratio, we need to bring the particle size to a smaller type. Okay. And for that we have the supported catalyst, where we take the advantage of high surface area support and we deposit the active material on this high surface area supported catalyst. So, these are some of the examples. So, for the bulk metals, I am just showing in same image of a silver catalyst, which is typically used for ethylene oxidation reaction. We have the supported metal catalyst, and in this image I am showing a platinum on high surface area silica support, and we can see that the particle sizes are of different nature. So, they can be single atom, they can be small clusters of couple of atoms, or they can be nanoparticles of few nanometers. We have metal oxides. So, there are bulk metal oxides where the surface is directly participating in the reaction, and the bulk is like indirectly supporting or providing some of the oxygen to the surface. And we have the supported metal oxide catalyst, and here is an example for supported tungsten oxide on high surface area zirconia. And also we can see we have like single atom tungsten, which are typically called the isolated tungsten centers. We can have dimer, trimer and long two dimensional sheets, and at the same time we can have tungsten oxide that is L03 nanoparticles as well. Okay. And there are few other categories like metal sulfides and nitrates, where instead of the oxygen we have the sulfur or the nitrogen bonded to the metal. So, this is one example of moly sulfide catalyst, pretty famous for dehydrogenation reactions these days. And then the same moly oxide, now we have it deposited on a high surface area alumina support. And as we can see, some of the areas as marked 1, 2, 3, 4 and 5, these are like the planes of the moly sulfides as seen as the fringe patterns kind of things. Okay. So, with that, let us just look at how big are these catalysts as compared to the reactor where they are doing the catalysis reactions. Okay. So, the industrial reactor, they can be of the order of tens of meters to hundreds of meters. So, they are pretty big in size, whereas the catalyst that is loaded inside the reactor, they are of the order of few meters, and the catalyst pellets are of the order of only millimeters, and the particles are of the order of microns. And now, just as a reference, the thickness of the human hair is in between 1 to 10 microns. So, these particles are that thin. Now, the active site on these particles are even smaller, they are 1,000 times smaller than this. So, of the order of nanometer, and if these are isolated atom or clusters of only couple of atoms, they are sub nanometers like few angstroms. so on. Now, the point is that's just not the only case. If we look at one of the schematics of the metal oxide catalyst, and by the way this is not just a representative catalyst, and the metal oxide catalyst like they compose more than 50% of the industrial catalysts. So, they are real in nature, and what we see is that on the catalyst there can be of different types of sites. You can have redox sites, you can have different types of acid sites. It can be a bronze acid site, it can be a Lewis acid site, there can be defect sites, there can be vacancy sites, and all these sites they take part in the reaction to a different extent. So, it may happen that all of these sites are participating in a reaction, or it may happen that only a few of these sites are actually participating in a reaction, right? And it can happen that some of these sites are giving us the favorable product, and some of these sites are giving us the undesired product. So, as a matter of fact, we need to know which site is giving us the selective product and which sites are giving us the unselective product. And once we figure out that, we can populate the surface with the selective sites and suppress the unselective sites. And for that, we need to know the structure activity relationship, and which is the essence of catalyst design. And to understand that structure activity relationship, we need to understand how the catalyst functions. And that is how this course is defined. We are going to look at the surface and the bulk of the catalyst during reaction, such that we know how these sites, what are these sites and how these sites are functioning or participating during the reaction. Now, this was the case of a metal oxide catalyst. We can have supported metal catalyst as well. Now, in cases if there are big metal nanoparticles, we can have flat surfaces of arranged atoms, which are typically known as the terrace sites, and on the terrace we can have one defect which is called a hole on the terrace, or we can have an extra atom which is called an add atom, a couple of atoms which are called add islands, and there can be an abrupt growth breaking of one plane over the other planes, which are typically known as the step sites, and we can have the corner or the king sites. Now, all these sites are energetically different towards the adsorption of the reactant, and this is something that we are going to discuss in the following slides. And because of that, for example, we have a diatomic molecule, it can be adsorbed on the top of one atom, it can be adsorbed as a breeze between two atoms, or it can be adsorbed on a threefold site or on the terrace of this whole flat plane. And there are possibilities, it can be adsorbed through one bond, or it can be in a bidentate form kind of things, where the two bonds are connected to two atoms of the catalyst which are placed next to each other. So, these are some of the things that we need to understand to know how the catalysis works, and for that we need to have different types of characterization techniques. But then what we discussed previously is that for a long time it was known that the catalysts, they do not change during the reaction, but the modern days catalyst, especially if it is a heterogeneous catalyst, and there is a fair chance that the dynamic is going to happen because of the reaction environment, because what we see at room temperature open to atmosphere condition, and when we do the reaction where the temperature is different, the pressure is different, the gas environment is different, the transformation will take place. So, here some of the examples in a cartoon form how these transformations may happen, or what are the typical ways the catalyst active site dynamics happen. So, we have the fresh catalyst, we have a distribution of different sizes of active particles on the catalyst, then it can actually restructure during the reaction, that is one. Number two, it can be leached from the surface of the catalyst, and there was a very beautiful example if you remember. So, platinum is platinum on supported platinum catalyst, those are used for the automotive catalysts, but because of high exhaust temperature from the from your vehicle, some of these platinums continuously fly off from the support, and over the time your platinum concentration of the surface goes down, and the process deactivates over time. Okay. It can happen that there is sintering is happening, which we will see an example in the next slide, where some of the smaller particles they come together to form a bigger particle. We can have the support hydrolysis or the collapse, where the support oxide structure is changing from one phase to other phase, or its surface area is collapsing time upstream on the reaction thing. We can have different kind of poisoning. We can have carbon deposits on the active material such that the access of the gas to the active material is now restricted, which can cause the deactivation of the catalyst. Or we can have some side products or the impurities in the gas stream which have much higher affinity to stay on the active surface such that they hinder the access of the actual reactant to the active surface, which is typically known as poisoning. Now, let us just look at one example of sintering. So, here this is an time resolved environmental TM image of the catalyst where we have the nickel that is deposited on magnesium aluminate, and we are looking at the catalyst structure evolution at 750 degrees Celsius in a typical hydrogen to water ratio of 1, and since the TM experiments are conducted under vacuum, so the pressure here is about 3.6 millibar. What we see is that at time 0, we have couple of bigger nickel particles, but we have a bunch of smaller nickel particles that is present. But with time, we can see some of these smaller particles have come together to form a bigger particle, and with more time on stream, now the smaller particles have almost disappeared. Their population has gone down significantly, whereas the population of the bigger particles has increased. So, this is one typical example of sintering, and then we will see like many of such examples how the transformation of the catalyst surface and the catalyst active site or the active phase is happening during the reaction by taking examples of different catalyst and reaction systems and via different characterization methods and mostly physical characterization methods. Now, some of those changes that we discussed a couple of slides back, I mean they have a length scale and the time scale associated to it. I mean the active site dynamics that just happen at a very small scale because the active sites are really small in size, and their transformation is really fast of the order of picoseconds. Whereas the segregation or the sintering processes, they happen at a slightly larger scale and they take long hours on the stream for those things to happen. So, this is you can actually look at all these time versus the length scale thing and what are the different transformation that is happening just as a fun. There are also transport limitations. We have transport at the reactor scale, we have transport to the sites, and all these things happen at different length scale as well as the different time scale. Now that we know the active sites are dynamics subject to the condition of the like reaction environment as well as temperature, can we use those things to help us? So, one example would be like, can we tune the temperature or can you tune the environment such that we will end up in preparing a certain type of catalyst which is going to be beneficial for us. So, these are like a couple of examples how the catalyst tuning can be done. So, typically how we prepare a catalyst is that we have a large surface area support. This is for example for a supported catalyst, and then we deposit the active material on that large surface area support and do some treatment on that thing. So, what we can do is that we can change the nature of the support. I mean it can be different crystal phase of the same material, or it can be just a different material, or it can be a mixture of two different materials. And because of that, the interaction between the support and the active phase that is present on the support is going to be different, which will ultimately affect the overall activity as well as the selectivity towards the product. And there can be the effect of particle size. We can have the deposited active material of very small size or very large size. I mean for some reactions the small size particles they favor a certain reaction, whereas the large size particles they favor a different kind of reactions, because the exposed facet from a smaller size particle like an isolated atom versus the exposed facet from a large scale particle are going to be different, and these facets are going to interact differently with the incoming adsorbate reactant molecule, and then the conversion will be to a different extent and to in a different route. Or what we can have, instead of just one type of active material, we can have a mixture of active material, 2, 3 or 4, there is no limit on that. So, some of these things can tune the properties of the original active material in different ways. They can be structural promoter, they can be functional promoters as well, and we will see some of these things throughout the course. Now, the other thing is there can be different types of treatments. So, these treatments can be just a thermal treatment, it can be treatment in a reducing gas, it can be treatment in a very specific type of gases, or it can be a cyclic treatment of reduction and reoxidation. And because of these treatments, the catalyst active site evolve over the time and will result in a certain phase which is different than the original phase, and now it can possess a different type of activity. So, we will just see one of those examples, the last one here, which is called adsorbate mediated transformation of the catalyst. And this is a very nice example how we can treat the catalyst before we can put it inside the reactor for the actual reaction, and then see how those treatments can affect the overall activity as well as the stability of the catalyst. So, here I am showing an example of copper zinc oxide that is deposited on alumina catalyst. This is a commonly used industrial catalyst for low temperature water gas shift reaction for methanol synthesis as well for methanol steam reforming. So, what we are doing here is that we are doing two different types of treatment. So, in the first phase, we are reducing the catalyst in an hydrogen environment for 60 minutes, and in the second case, we are reducing the catalyst in a hydrogen environment for 50 minutes, followed by treating it in a mixture of methanol, water and hydrogen for 10 minutes. And we have the high resolution TEM image on the left to see these two different treatment treatment, how they are ultimately resulting a structural evolution of the catalyst. So, in the first case, what we have is that we have the aluminum support present as it is. The copper is present in metallic form because we reduced it hydrogen for 60 minutes, but the zinc is present in the zinc oxide form. It is in a +2 oxidation state, and this is actually the like verified by the electron L03 loss spectroscopy, and this is one of the techniques that we are going to cover in this course as well. Whereas, if we treat it in hydrogen for 50 minutes followed by treatment in methanol, hydrogen and water, what we see is that part of this zinc oxide, now they migrate to stay on the top of these copper nanoparticles as seen from the image. So, in one case we have the zinc oxide and the copper oxide, they are present next to each other on the alumina support. In other case, the zinc oxide and the copper is present, but now a part of the copper is actually covered with some form of zinc oxide, ZnOx. So, if we look at that, these two catalysts, how that is affected, how that is reflecting, well, I mean these two different treatments, how that is reflected on the catalytic activity, we see that the initial activity is not very different. However, if we put the catalyst for long hours on the reaction environment, which is for 40 hours, we see that the catalyst which was treated just in hydrogen is deactivating over the time, and a 35% loss to the initial activity has been observed for a 40 hours of operation or 40 hours on time. The other one is like decreasing only by 10% as compared to the 35%. So, this shows that this different kind of treatment to form this SMSI effect, which is called strong metal support interaction, where you have an inverse structure where the metal oxide is now present on the or partially covering the metal, is more beneficial towards the long term stability of the catalyst. Okay. So, that brings me to the end of this section of the course. So, let us just go over the things that we saw, is that all of us are convinced that the catalyst and catalysis are going to play an important role in the 21st century, and the structure of the catalyst is not simple, it is rather very complex, as we saw some of the examples from supported metal catalyst as well as supported metal oxide catalyst or bulk metal oxide catalysts. And the active sites are dynamic in nature. We saw some cartoon diagram how the active sites can change over the time, and we also saw that how we can tune the nature of the active sites to actually help or actually cause our reaction to go in a more positive directions. And that brings to the the major point is that we need to understand how the catalyst works, and for that we need to understand what is the active structure, what is the active site, and how they are functioning to establish the structure function relationship. And once we have that, we can use that knowledge to design a better catalyst. And for that, what we want is that characterization of the catalyst during the reaction conditions, and on which the whole course is actually built. And so, before going to the next lecture, maybe we can take about 5 minutes to go over the concepts that we just learned, and then if you have any questions, I'll be happy to answer them. Okay. In the last lecture we discussed how the catalyst surface dynamics happen, and then here we will see a few more example about the surface dynamics, as well as we will go I mean just as a primer to the surface reaction and the surface poisoning, and how we can identify those things from a chemical characterization point of view instead of a physical characterization point of view, such that I should be able to convince that the physical characterization techniques are going to be, well, the chemical characterization techniques are going to be as important as the physical characterization techniques in understanding the surface and the bulk structure of the catalyst during the reaction. So, moving forward, I will introduce another concept which is called the Savart principle, and as we know, adsorption is important for catalytic reaction. So, without adsorption, the reaction cannot happen. So, what happens is that we have the gas phase species present, there is diffusion in the gas phase, then there are molecular adsorption or dissociative adsorption, then there are surface diffusion, which is nothing but hopping of the adsorbed molecule from one site to other site because they possess some thermal energy. Now, because of the energetics of the surface, and if there is another gas molecule present, or it can be just a single atom reaction, they get converted to a different species on the surface of the catalyst, which then ultimately dissolve to the gas phase, and that is how the reaction happens. But now, what Savart suggests is that if the reactant is really strongly adsorbed to the surface, then of course the desorption will not happen, correct? And the rate of the reaction will be really low. On the other limiting case, if the adsorption is not strong, then there won't be enough reactant that is present on the catalyst surface for conversion, and hence your rate is again limited. So, there has to be an optimum where the adsorption binding strength is strong enough for getting a significant conversion, but not so strong that the desorption cannot happen. Okay, and that is where the maximum come, and it is called the Savart maximum for the reaction. So, the reason I introduced to the adsorption is that we were going to talk about how the surface reconstruction happens, and when we have these ordered, well, I mean these adsorbed molecules present on the surface of the catalyst, how their structures are defined based on the type of the surface and as well as the concentration of the already pre-adsorbed substance on the surface. And from that we will look at how the catalytic reactions happen, and we will go into some detail about the surface poisoning with one example for the CO oxidation reaction. Okay. So, this is just a very cartoonistic form, like what can happen when a gas molecule that is bombarded on the surface. I mean, it can just elastically scatter, it can inelastically scatter after losing some energy after bombardment on the surface, or it can be present in an adsorbed state, which can be a Fiji-Stauff state or a precursor state on the surface, or it can be in a chemical bonded state to the surface. Now, once it is chemically bonded to the surface, there can be possibilities of different surface hoppings. That is because the surface is not of a continuum energy. The energy is continuously changing because the structure is not constant, and the atoms at the atomic level possess different energy and they have a certain distance between them. and they can be converted into a different product, and the product can dissolve. There can be a couple of different types of gases that is coming. There can be single atoms, those are coming and combining and going back. So that is like a rough I would say rather a broad way of what happens when one of the gas molecules that comes in contact with the surface of the catalyst. So just because the surface is non-ideal, there can be multiple type of adsorption site. There are some sites which has a higher preference for the adsorption of certain molecules because of their energetics, where there can be certain sites which are not very preferable. And there is of course a non-uniform energy distribution. There is of course an effect of temperature which determines how much of these molecules can stick to the surface, and of course the pressure, and is there any other species that is already pre-adsorbed on the surface. The surface is nothing but the adsorbate as mentioned here. So this is how do we define that, how much of these gas molecules are actually going to stay on the surface, and what are the different parameters that we just discussed in the previous slide. We will just see that as an example, and there is a parameter called the sticking coefficient, which actually determines how much of these molecules are going to stay on the surface or stick to the surface. So by definition, the sticking coefficient is nothing but the rate of adsorption upon the rate of bombardment. So rate of bombardment is nothing but the total amount of reactant or the adsorbate that is bombarded to the surface, and the rate of adsorption is a fraction of that total amount which is staying on the surface, okay, and that is known as the sticking coefficients. Now by definition, the sticking coefficient value should be between 0 and 1. 0 means for whatever gases or the amount of the gases that is bombarded on the surface, nothing is going to stick on the surface, and 1 means everything is going to stick on the surface, okay. So these are some of the typical ranges. So on clean metal surfaces, if we have gases like hydrogen, CO, oxygen and nitrogen, the sticking coefficient is typically between 0.1 and 1. But this can be really low. For example, if I have a polycrystalline surface, and here is an example of polycrystalline silver surface, and I am trying to adsorb oxygen on it, the sticking probability is now between 10 to the power minus 3 to 10 to the power minus 4, which is really low, and these ones are going to affect how my reaction is happening. So the sticking probability, that depends on the nature of the surface, the type of the exposed facet of the same substrate or the adsorbent, the surface coverage, that means how much of these adsorbate were already present on the surface, the temperature and the pressure as well. And the first three, we are seeing an example here on the right hand side plot, where we are looking at the sticking coefficient on the y axis as a function of the surface coverage, which is given as atoms per centimeter square of the surface area, of nitrogen on different facets of tungsten at 300 Kelvin. And as you can see, we have tungsten 100, 110, 111 and all different kinds of facets, and the sticking coefficient is different on that. But at the same time, the sticking coefficient is not constant throughout the surface coverage. As the surface coverage is increasing, of course, we are the number of available sites for taking up more gases is decreasing continuously, and that's why my sticking coefficient goes down as a function of increasing surface coverage, okay. But the measure point from this thing is that even if we have the same tungsten surface, depending on what is the type of the facet that is exposed to the atmosphere or exposed to the gas molecule, I can have different amount of gas adsorbed, okay. Even for a clean surface, when there was nothing adsorbed, that is a surface coverage of 0 for different planes, we saw, and what we were discussing is that the surface coverage is of course one factor that defines how much of the gases that can be taken up by the surface, but most importantly what I wanted to show here is that even for the same metal, if we are exposing different facets, the sticking coefficient is going to be different, because different facets has a different energetic and they are going to interact with the incoming molecule differently in general. Okay. Now let us see do we actually see any change to the surface because of that? Okay. So, on the left hand side, I have a clean tungsten 001 surface, but this is at room temperature. But if I take it to low temperature, now what I find is that the surface layer has a different mesh than the bulk which is present below it. That means temperature is one factor which can affect the nature of the surface, whereas the whole bulk can still be present in the original form. And the other way, without changing the temperature, if we are taking the same tungsten 001, but now we are adsorbing gases at the same temperature, then also because of the presence of these adsorbed gases, we are changing the nature of the surface atom arrangement. Okay. That means we have two things here. Number one, the temperature can induce the restructuring of the surface. The adsorbate can induce the restructuring of the surface. And the bottom line is, any solid which is typically considered rigid is actually not rigid. Because of the temperature and the presence of adsorbate, the surface phase can change. And here I am showing another example, and this is for gold 110 surface, and as we are seeing that the surface is not present in the 110 form, but rather it is a C2 cross 1 type of geometry. And then as we know, all these atoms or the molecules, they have certain vibrations associated with them because of the temperature or the thermal energy. Now, if the temperature is high enough, that means the thermal energy is high enough, then the vibration will be at a much larger scale, right? And once that mean square displacement from the original position or the atom position is more than 1/10 of the atomic distance, the surface does not stay rigid anymore. It just behaves like a fluid, which is called the melting of the surface, whereas the bulk is staying as the same configuration, but the surface, just because the coordination of the surface atoms are different than the bulk atoms, it is going to be very different than the bulk. So, when we are using a bulk characterization technique and stating that okay, we have this certain phase present, but the surface might be at a different phase. Well, I mean, very likely it is that the surface is at a different state or a phase than the bulk. Okay. And this is where we are going to see more and more examples throughout the course, how by identifying, well, how by characterizing with a bulk technique versus a surface technique, we can see how the surface is different than the bulk, and then that helps us in understanding the catalysis phenomena much better as compared to when we are using just a bulk characterization technique. Okay. Now, the adsorbates which are on the surface, they are also going to take different steps, okay, or different arrangement. And for that, I mean, what we were talking previously is the coverage of the surface. Similarly, it is just defined by the formula that the surface coverage theta is nothing but the number of adsorbed species upon the number of atoms that is present on the outermost layers. Okay. That means the total number of sites which are available for the gas adsorption and how many of those sites are actually taken up. That is nothing but the surface coverage. Okay. And here is one example, is that this is an dissociative chemisorption of oxygen on tungsten 110 surface, and what we are seeing is that when we are changing the temperature as well as when the surface coverage is changing, which varies between 0 and 1. 0 means all the sites are empty, 1 means all the sites are taken up by the gas. We are seeing that like different arrangement of the oxygen atom on the surface is present. It can be a P2 cross 1 type of mesh, it can be a P2 cross 1 and a P2 cross 2 combination, or it can be a de-ordered space type of things. So, what the lattice gas model suggests is that the surface is constant, but what we are seeing here, the solid surface can be considered as a rigid matrix of, that is the lattice gas model that says the solid surface can be considered as a rigid matrix of discrete sites for adsorbed species. But now this can be true only for the Fiji-served species, but may not be true for the chemi-served species, because on the previous slides we saw that because of the chemisorption, the surface rearrangement is going to happen, and the chemi-served species or the adsorbate on the surface can themselves be arranged in a particular order, or they can be in a disordered state, and that ordering depends on the temperature as well as the surface coverage of those adsorbate on that particular surface. There are few more examples why we have a P versus C type of structure. For example, we have, okay, so here the empty circles are the adsorbates, which is nothing but the gas molecules, and the solid circles are the adsorbent, which is nothing but the catalyst surface. Okay, and we can see on the solid sorbent we have the adsorbate that is taking up different arrangements, and how these different arrangements are defined. I mean, I do not want to go into the details, but there is a little bit of theory on behind these things. Of course, if we have the epsilon 1 and the epsilon 2, which are the two interactions between the neighbor and the next to next neighbor, they are usually going to be repulsive because they are pretty close to each other and because of intermolecular repulsions. But the E3, which is next neighbor, can be an attractive force, the interaction, or can be a repulsive force, and that defines what my surface mesh structure is going to be. But this is just an example. We are not going into the details of such things, but we will look in the case of heterogeneous catalyst, supported metal, bulk metal, supported metal oxide, bulk metal oxide, how the surface is changing and continuously evolving during the reaction or because of the environmental conditions. So, and then the add layers can be of different types. So, this is an example where we have xenon, krypton or methane that is adsorbed on graphite at a very low temperature, and they can exactly take up the structure of the graphite beneath it or on which they are getting adsorbed. So, this is something called a commensurate add layer, where the surface of the structure is taken up by the arrangement of the gas molecules that is present on the surface or adsorbed on the surface. But there can be non-commensurate add layer where things are not exactly on top of each other. For example, it can be a threefold site here where the adsorbed species is attached. It can be on a twofold site, it can be on a fourfold site, or it can be on a top sites. So, all these different types of things are there, and these are called the coincident structure, for example. Now, there are just last couple of examples. What we are seeing is that we have chromium 100 surface present, and on that we are actually adsorbing chlorine, and what we are seeing is that exposure to the different amount of chlorine, the arrangement of the chlorine on this chromium 100 surface is changing. And couple of examples as a demonstration are shown here. If I have a surface coverage of 0.5, then the surface mesh structure of the chlorine is a C2 cross 2 type of geometry, whereas for a surface coverage of 0.8, it is going to be a P2 cross 5 of geometry. Now, there is just one more concept that I want to add to this thing, because this is something that we are going to see in one of our future lectures, is that the same thing when we have the chromium 100 surface and we have the adsorbed chlorine on the chromium 100 surface, but now we are adding sodium to it. So, we have arrangement between the sodium and the chlorine atom. There is a typo here, this is not carbon, this is chlorine, Cl. So, there is an arrangement between the sodium and the chlorine atom, and they take up the exact structure of the chromium 100 surface, and this is like the sodium chloride, they are arranged as exactly to the chromium 100 surface, and they are called in registry, or this type of phenomenon is called epitaxy, where the growth of the crystal on a particular surface is determined by the orientation of the surface. So, one such example is V2O5 on titania. Now, titania can have different crystal phases, and the typical ones are anatase and rutile. And then when V2O5 grows on anatase versus it goes on rutile, in one case we see the epitaxy formation, whereas in the other case we do not see it. And when that is subject to the reaction, for example, orthoxylene to phthalic anhydride, we see one of these phases is going to be more active as compared to the other phase of titania. It is the same titania, but now I have an anatase phase versus a rutile phase, just because the surface structure is different. The vanadium oxide, which is the active material for this reaction, that has grown up on the surface differently because of the different surface nature, and that results in a different activity. Okay. Okay, so let's just review these things a little bit what we have covered so far. That surface reconstruction happens. So the surface cannot be considered as rigid, and this reconstruction can be induced by temperature as well as by the adsorbents. Now the adsorbents on the surface, they can be of disordered layers or they can be of ordered hard layers, and their ordering varies on which they are grown as well as the coverage of the surface as well as the temperature. Now with that, next we will go into a little bit on the primer on the catalytic reaction as well as the surface poisoning phenomena and how we can implement a very niche chemical characterization technique to identify the surface poisoning and then to suppress it. Okay. Okay, so this is C cross 2 cross 2, you can have 2 atoms like this and then everything is repeated after that, right. So, that is called, so similarly C 2 cross 4, if you go by the 4 units here and 2 units on this side, then everything will be repeated by this. So, that is how it is just defined. It is just the minimum arrangement after which the repetition is happening, just like the unit cell type of thing. Okay, so this is something that we saw previously, and what we identify is that adsorption is must for catalytic reaction to happen, and the typical two classical examples are an Langmuir-Henselwood type of adsorption as well as an Illy-Riddle type of adsorption. In Langmuir-Henselwood, we have two different reactants A and B, both are adsorbed on the surface, and the adsorbed A and the adsorbed B, they react, they form a product C, which then goes to the gas phase by desorbing. Okay. In the Illy-Riddle mechanism, which is a very limiting case of Langmuir-Henselwood mechanism, where one of the two reactants is actually adsorbed, the other one has a very low adsorption power or the sticking coefficient. So, in that case, A is limited by the adsorption, where B is adsorbed on the surface, and the A in the gas phase reacts with the adsorbed B to form the product C. This is just a primer to show the difference between the Langmuir-Henselwood and the Illy-Riddle mechanism, and we will just go with one example how the presence of one reactant can actually hamper the adsorption of the other reactant as an example of surface poisoning and how we can avoid that. Okay. So, for that we are taking a case study for CO oxidation, and this is some computationally generated diagram for rhodium 111 surface, and we can see the red ones here are the CO molecules and the blue ones here are the oxygen atoms. Okay. The CO prefers to stay on the top sides. So, that is exactly on the top of the rhodium atom in a specific configuration. Okay. Whereas, the oxygen prefers to stay on this threefold hollow site of thing. Okay. Now, what happens, just because oxygen is getting adsorbed on the surface by a dissociative adsorption, so we need two sites next to each other available for the oxygen to come to the surface and then dissociatively adsorb and then adsorb on these two sites. Okay. Now, if we look at this diagram where both CO and oxygen are adsorbed, as you can see, if the surface is fully covered with CO, I mean not exactly fully, but to a great extent or significant extent, if it is covered with CO, then the oxygen to be adsorbed at one side and then get dissociated and transferred to the other side, such that the two oxygen atoms after dissociation can take up two places, it has to go through a nearby CO species, and that is going to be energetically hindered. Okay. So, what happens is that when the CO has a much stronger affinity to bind to the rhodium surface and significant amount of the rhodium surface is covered with CO, then the oxygen adsorption is hindered and the reactivity goes down. Unless oxygen is hindered, the CO cannot react with the adsorbed oxygen, it cannot do the oxidation reaction, that is the CO2 formation. Okay. So, how to find these things experimentally? For that, we are just giving an example here. Well, I mean another chemical probe technique, which is called temporal analysis of product, and this is just a diagram. So, I will take a minute to explain this to you. So, what happens is that we have a microreactor present, and inside that microreactor at the center of the microreactor, we have a thin bed of catalyst that is present. And the top of the reactor and the bottom of the reactor, they are just filled with inert materials. Okay. And then we have pulse valves and we have a flow valve, that those are connected to the inlet of the reactor, such that the gas can be either flown or pulsed into the reactor system, and then the product or the unreacted reactants, they can be detected through a mass spectrometer, which is situated just next to the exit of the reactor. Correct? Now, there are few advantages of using the pulse system in a tap reactor as compared to in a flow system, is that, I mean, we can do a steady state experiment if we are doing the flow, like a constant feed of the reactant gases, or we can do a transient experiment. Transient means something that is changing with time, and in this case that thing is concentration, that is changing with time. So, if we have a pulse, the concentration of the reactant that is going to the reactor is going to change with the time, that is why we are calling it a transient experiment. Okay. So, we can pulse it, but then we have more capability, we can operate at high vacuum condition or we can operate at high pressure conditions as well. Okay. But in this particular example, what I am going to show in the next couple of slides, we are going to operate the reactor in a high vacuum condition and in transient mode. That means the reactor itself is in an ultra high vacuum condition and we are giving pulses of reactant to the reactor. Okay. Now, look at the pulse size. So, this is the typical range. We have 10 to the power 13 to about 10 to the power 17 molecules per pulse, and the pulse width is really small. It is about 50 to 250 microseconds. So, it is like a small delta function, but at the outlet of the reactor it will look like a pulse. Okay. Now, the advantage of this thing, well, I mean, if we go by the Avogadro's number, 1 mole is nothing but some 6.023 into 10 to the power 23, and here we have almost 10 orders of magnitude lower. And any guess what is the typical concentration of surface atoms on any oxide or metal support or metal catalyst? Just guess a number. Okay, so I'll just give the answer. So, it's roughly 10 to the power 15 atoms per centimeter square, and what we are doing is that we are pulsing 10 to the power 13 molecules. So, now look at the total number of sites that is available, and the amount of reactant that we are pulsing in is 1% of that, and on top of that the reaction or the adsorption is not 100%. So, taking an efficiency of 10%, actually there is 3 orders of magnitude difference on the number of sites that is occupied with one pulse as compared to the total number of sites that is available. Okay. So, if that part is clear, what I am going to tell next is that just because you are going to run this reaction in a vacuum condition, what happens is that your gas-gas collision are going to be negligible, because the vacuum is so high, the concentration of the gas molecules in a particular volume is so low that they are not going to interact with each other. Their mean free path are so high such that there will only be a gas surface collision, and when I am saying it is a gas surface collision, the surface is nothing but the surface of the catalyst. Okay. So with the tap technique, what we can do is that for some reactions where the gas-gas contribution are also I mean the gas-gas reaction is also contributing to the overall reaction, we can actually decouple the gas-gas contribution and the gas surface contribution, and we can look at the kinetics of the catalyst, okay, by avoiding everything on the gas-gas part. Okay. So, let us just take an example what are the different types of experiment that we can do with the tap. As we know, like with one pulse we are addressing only a very small fraction of the total number of available sites, correct. So, there is single pulse experiment. What we do is that we give one pulse, we look at the product, we give another pulse, we look at the product again, and what I can do with one pulse, I am addressing only a very small portion of the total number of available sites. And if I keep on pulsing say 1000, 10,000 of such pulses, now I am addressing the whole catalyst, and with each pulse I can look at the product evolution. And so, from pulse, so So, from pulse 1 to pulse 2, just because we are addressing a very small fraction of the total number of sites, there is not going to be a significant difference, because it is a very small fraction. But pulse 1 versus pulse 10,000, there is going to be a significant distribution, a significant change, correct. And then what we are seeing is that with series of pulses, we can actually look at how the catalyst structure is evolving, and based on that, how my product distribution is changing. That is what just roughly shown as an example here. So, maybe with increasing pulses, we are taking up a particular type of site such that my conversion is going down and down, because the reactant concentration at the outlet is higher, that means the conversion is lower, right. So as my product formation is decreasing, okay. But then it can also have that the product selectivity might vary. If I have multiple products, because the sites are changing continuously, initially if I have selectivity towards product P, then after say 1000 pulses, maybe my selectivity will go towards product Q, say for example, okay. And then there is another type of experiment here, which is called a pump probe experiment. So, pump probe, in simple word, we pump one reactant, we allow that to settle on the surface of the catalyst, then we probe with the second reactant, okay. Say for example, if you are doing a oxidation reaction, we pulse oxygen first, we allow the surface to be covered with oxygen, then we pulse our hydrocarbon, such that it can react with that adsorbed oxygen, which has already taken up some time to equilibrate with the surface or the surface of the oxide phase, and then we look at the product. And in such cases, we can do a pulse probe type of experiment. Okay, so if this part is clear to you, then I am going to show one example for the CO oxidation and how we can look at the poisoning thing that we are discussing couple of slides back, that if CO has taken up majority of the sites, then there is no room for oxygen to get adsorbed dissociatively, and hence the reaction is restricted. Okay, so here I am taking one example for supported platinum catalyst, which can do CO oxidation reactions, okay. And just look at the 4 quadrants. I have graphs at different conditions, okay. The top 2 quadrants versus the bottom 2 quadrants, it is pretty simple, they are at 2 different temperatures. The top 2 are conducted at 54 degrees Celsius, or the bottom 2 are at 190 degrees Celsius. Okay. Then the left 2 and the right 2, there is a difference. So, in the left 2, what we are doing is that first we have given a series of CO pulses such that my catalyst surface is now saturated with CO. Then I am pulsing oxygen, and what I am trying to figure out is how much of carbon dioxide, which is my reaction product, forming because of the oxygen pulse on a surface which is already pre-covered with CO. Okay. In the other case, it is just the opposite. I cover the surface with oxygen, then I inject CO such that the incoming CO is now going to react with the adsorbed oxygen on the surface, and what all we are looking in all these cases is nothing but the amount of CO2 formed. Okay. So, now there are certain difference. Okay. Let us just start from this one. My surface is pre-covered with oxygen and I am giving CO. So, from the very first pulse, I am seeing the formation of CO2, and that just goes on and then dies out, because the amount of oxygen on the surface will deplete over the time. So, we are taking that up with each and each pulse, and that is why my activity goes down. But in the opposite case, if I see here, the surface is pre-covered with CO and now I am pulsing oxygen, I am not seeing CO2 for about 300-400 pulses. So, that gives us an idea that once the surface is saturated with CO, the oxygen cannot be adsorbed on the surface, and if oxygen cannot be adsorbed on the surface, the reaction cannot happen. But then what is changing or what is different at 190 degrees Celsius? The same thing here, of course, this is a higher temperature, so the activity would be higher. So, the initial CO pulses on a oxygen pre-covered catalyst, we are seeing like the bigger pulse as compared to a lower temperature for the CO2 formation, correct. On the left side at 190 degrees Celsius, now even the surface is covered with CO, still with the first pulse of oxygen, I am seeing the formation of the product, that is CO2. Now, who can answer why that is happening between this and this? For bond to be dissociated, first it needs to be adsorbed. Okay, yeah. Desorption, not diffusion. Diffusion, okay. Okay, so I will take that as desorption. So, lower temperature that favors adsorption, higher temperature desorption is favored. So, when you are at high temperature, although you have pre-covered the surface with CO, because of the high vacuum condition of the tap and the high temperature as compared to 54 degrees Celsius, now some of those COs are loosely bound, not as strongly bound as in the case of 54 degrees Celsius. And because of that, now you have more available sites for oxygen adsorption, and hence your reaction just goes on. Okay? But our target is that we want the catalyst that is active at low temperature. So, what we can do? The simple answer is, can we add a promoter such that the CO binding affinity to platinum is decreased at low temperature, such that CO binding is not that strong and that does not hinder the adsorption of oxygen, and hence my reaction goes on. Okay? And that is exactly what the authors did. They added chromium oxide as a promoter to the platinum silica catalyst, which we just saw in the previous slides. But now, even if we are at 40 degrees Celsius, I have the oxygen pre-covered surface, we are pulsing CO, definitely we are seeing CO2 because it is oxygen pre-covered surface, and oxygen covering of platinum does not hamper CO adsorption. That is what we saw here, right. Once we have the oxygen pre-covered, it does not hamper CO adsorption, but once we have the CO adsorption, it actually hampers the oxygen adsorption. But in the other case, when the surface is pre-covered with CO and now I am giving oxygen, I am still able to see product even at a much lower temperature, which I was not able to see in this case. Okay. So what is the conclusion? The CO binds to platinum strongly, and at low temperature, if significant of the platinum sites are taken up by CO, then that hinders the oxygen adsorption. But at high temperature, just because the binding energy is lower, because desorption is more favorable, we do not have that kind of issue and the catalyst becomes active. But if we are adding the chromium oxide to this platinum as a promoter, now what we have is that the chromium oxide is suppressing the CO binding to platinum, and hence we can still see the product formation or the reaction to happen even at a much lower temperature, which was not happening previously. And here is just the table that shows you have only the chromium oxide, the mixture of platinum chromium oxide and just the platinum oxide, and we can see the area of CO2 is nothing but corresponding to the amount of CO2 that is formed. Okay, just because it is a pulse, they are taking the area, not the rate. Okay. And you can see even at 25 degrees Celsius, we are seeing product which are not observable in this case. Okay. Okay, so that brings me to the end of this lecture. So the catalyst surface is not rigid but dynamic in nature, and that dynamics depend on multiple factors, temperature as well as the nature of the adsorbent that is getting adsorbed on the surface. Okay. And the physical characterizations are really powerful, which we just saw in the previous slides, that some environmental TEM as well as electron energy loss spectroscopy and some of the other characterization technique, vibrational optical spectroscopies and X-ray based methods, which we are going to see throughout the lectures, are capable of looking at the surface dynamics as well as the bulk dynamics of the catalyst during the reaction. But in addition to that, we also need a chemical probe technique, for which I gave the example of temporal analysis of product, right. And a combination of both are going to give us the structure activity relationship, which will help us for the catalyst design. So, which I am just going to summarize in a couple of slides. So, if we go back to our original length scale diagram, the reactors are pretty big, whereas the active site on the catalyst are really small in size. But now the question is, if something is that small, I mean, how can we see it? That is number one. And on top of that, how can we figure out how they are functioning? Correct? And for that, we have a bunch of characterization techniques, and this is a list and with different temperature pressure limit as well as the acquisition time, spatial resolution and all. And among all these techniques, the optical techniques like Raman, IR, that is infrared, and UV visible spectroscopy are the most popular ones because they are the benchtop techniques which can give us molecular level information at reaction condition or during the reaction. Okay, and Professor Banares is going to talk about these three techniques a lot throughout the course, and I will be covering those parts a little bit, and I will be covering the other parts as complements to these three techniques throughout the course. Okay, in addition to these physical characterization techniques, we have a bunch of different chemical characterization techniques. For example, we have chemisorption, we have temperature program experiments, we have reactant step jump experiments, these are transient techniques. We have SITCA, that is steady state isotope transient kinetic analysis, we have modulation excitation spectroscopy and all. Now, all these techniques can be used on their own just with a product detector, or they can be combined with the techniques that I am showing on this slide. So, they can be run in an operando mode. So, you are looking at the dynamics of the product because of the transient input. At the same time, the effect of that transient on the dynamics of your active site can be captured simultaneously. Okay. Now, how we are going to apply these things, and this is where I am going to introduce the in situ operando experiment. So, we have our microreactor, like this is just a cartoonistic diagram, and we have small, say for example, fixed bed reactors where we load our catalyst, and this is isolated from the environment. So, we can flow gases, we can raise the temperature, and then we can shine different probes, and these probes depends on the type of the technique that we want to use. It can be beam of electrons, beam of ions, a laser beam, or it can be an X-ray beam, correct? And that gives us information about the surface structure, the type of the reactant intermediate or the surface adsorbed species that is present on the surface, and their dynamics and all these things. And then we complement those things with steady state experiments as well as with transient experiments. Now, these transients can be incorporated in multiple ways. Just like we discussed, it can be a temperature program experiment, it can be at different coverages, it can be a pulse, or it can be a transient of the isotopes of the same molecules. So, for the catalyst, the isotopes are not very different, but for us, when we are looking things from the spectroscopy sides or we are looking things from the product sides, there is a different signatures. Okay. And then when we combine these both techniques, what we get is a structure activity relationship which lead the path to the catalyst design. And that is what we are going to do throughout the course with different techniques, what is their power, and more importantly, what is the limitations of those techniques while we are applying these things, and from that how we can get information about the catalyst and catalysis science. Okay.